All right, let's look at how we find eigenvalues and eigenvectors. This is and over here. Okay, of this matrix, 3 by 3 matrix, and we already know what to do. We actually to find eigenvalues, we solve this determinant. So we have over here is a minus lambda I. Which means simply subtract lambda on the diagonal, and then this is what we have. It's a determinant we're going to find, and 2, negative 3, and 2, and 1 minus lambda, and negative 6, and negative 1, and negative 2, and 0 minus lambda is negative lambda. So we have this determinant over here to find. Okay. Now, row operations are not going to work because of these variables over here. So we have to use simply either use cofactor expansion or simply use the formula. Since this is 3 by 3, let's go ahead and use the formula. So multiply this out, it's positive. But we have a lot of negative signs, so be careful. Negative becomes positive. So this term actually turns out to be lambda times 2 plus lambda, and then 1 minus lambda over here. It's a positive term. Now this is another positive term. We have 2, negative 6, and negative 1. So 2 negative signs, it's positive. So this one is going to be positive 12. Okay. Look at this one over here. Negative 3, negative 2 is 6, and then times 2 is 12. So another 12 we have over here. Okay. Now, we have to go this way. It's negative, so let's first write down the negative sign over here. So now negative 3, negative 1 is 3, so we really have 3 times 1 minus lambda. We have 2 more negative signs. Let me put it over here. So we have 2 times 2 negative lambda. So we have really positive 4 lambda. So let's write down over here 4 negative lambda over here. And then these 2 is 12. And this is negative. And remember, it's negative sign over here. So we have negative and then 12 times negative 2 negative lambda. Okay. Now let's move over here a little bit. So we have multiply them out, and let's see what we have. We have over here lambda over here. We don't have to do it at once. Of course, we can do it on scratch paper, but let's try to see what we have. 1 lambda and negative 2 lambda, so we have negative lambda, and then have negative lambda squared. Okay. And here we have 24. Okay. And then next one we have negative 3, and then plus 3 lambda, and this is plus 4 lambda over here, and we have 24 over here, and plus 12 lambda. Okay. And let's try to multiply them out, all of them. And we have 2 lambda and minus lambda squared and lambda cubed. Now we can add them up. So we have over here 24 is 48 minus 3 is 45. Okay. And then 7 lambda plus 12 lambda, we have 19 lambda over here. But that's not all. And if we look at it, we still have something like this. We have negative, and we put the terms over here according to their degree over here of lambda. And then we have, this is now 21. So we can actually change this one to 21 now. And then plus 45 is equal to 0. Okay. In general, it's rather hard to find the roots for a cubic polynomial, but here we're going to try. Remember that 45 over here, we know 45, we can factor 45 into 5 times 9, right? And that's 5 times 3 squared. So we're going to try to see if any of these numbers are roots, plus minus 5 and plus minus 3. We learned these things in middle or high school over here. So let's try 5. Now, the equation over here, we can divide negative 1 both sides. So this one over here is really the same thing as lambda cubed and plus lambda squared minus 21 lambda and minus 45 is equal to 0. We're going to try to see if any of these numbers is a root of this equation. And we try the first one and we find yes. 5 cubed is 125 plus 5 squared is 125 plus 25 is 50. And then 21 times 5, that's 105. And then again 45. So this is again simply 0. So we have, so this is going to be a factor. So this one over here, 5 over here is a root. Okay. Now we remember if 5 is a root, that means lambda minus 5 over here can divide this polynomial. So we now do the long division over here. So we try to do the long division. Of course, you can always use Maple and other kind of computer software system to find these things, but let's try to review what we had before. And then we have lambda cubed, and multiply them out, it's negative 5 lambda squared. And this is what we do, remember, we subtract this one over here. So this is 0, and lambda squared minus 5 lambda squared is going to be 6 lambda squared. And then we have minus lambda over here and minus 45. Again, we remember this method is called long division. And now, because we have 6 lambda squared, so we have quotient over here 6 lambda, and then we multiply them out. It's 6 lambda squared over here. Distribute negative 5 times 6 is negative 30. So we have negative 30 lambda. And then we again subtract over here. What do? We have negative 21 minus negative 30. So we have 9 lambda over here and minus 45. Of course, it's divisible. So we have 9 over here. And we have 9 lambda and minus 45. And that's perfect 0 over here. So what it means is that lambda cubed plus lambda squared minus 21 lambda minus 45 is equal to lambda minus 5 and lambda squared plus 6 lambda and plus 9. So we will recognize over here it's a complete square, so we have lambda minus 5 and lambda plus 3 squared. And then we have 2 eigenvalues over here. We have 2 eigenvalues we have over here. Lambda 1 is equal to 5 and lambda 2. In fact, we have 3. This is called a multiple root. So we have over here, or a root with multiplicity 2. So this is going to be negative 3. This comes from over here. We are done with finding eigenvalues. Now we try to find eigenvectors. Okay. To find eigenvectors, we solve this equation over here one by one. So we have a minus lambda I over here, x is equal to 0. So let's look at first lambda 1 is equal to 5. So what we have over here is a linear system. We replace this lambda by 5, so we have negative 2 minus 5. So this is 7, negative 7. And then this one is 2, and this is negative 3, and this is 2. And then we have 1 minus 5, so it's negative 4. And then we have negative 6, and negative 1, negative 2, and negative 5 over here. Yeah, lambda is 5. So what do we have of something like this? x1, x2, x3 is equal to 0. Now we know how to solve a linear system, so we use the row echelon form of this coefficient matrix. So we look at this one over here. Now we have negative 7, 2, negative 3, and 2, negative 4, negative 6, and negative 1, negative 2, negative 5. Okay. Now, if you look at the textbook, they used fractions and things because they didn't know how to swap these. But we know we like leading ones, so let's multiply negative 1 to R3 first, then we have positive 1, and then swap with the first one. So we're going to do R1 and R3 swapping, and this is what we have. Okay, let's look at what we have over here. We have 1 and 2 and 5. Okay, and then still second one is not changed, so this is what we have. Last one is -7 and 2 and -3. Okay, so let's move over here to see what we need to do. Okay, now we have leading one over here, so we need to multiply -2 to R1 and then add it to R2. Okay, and then for the last one, we simply multiply 7 to R1 and then we add it to R3, right? That's what we have. And then we have 1, 2, 5, and then 0. Now -2 times 2 is -4, plus -4 is -8. And here we have -10 minus 6 is -16. And here we have 0, and 14 plus 2 is going to be 16 over here. And 35 minus 3 is going to be 32. Okay, and we see good things over here. So we divide R2 by -8 and then R3 by 16, and we get something really simple. We don't have any fractions, and this is what we have. And 0 and 1, 2. Of course, last step over here, we simply use -R2 add to R3, and then this is what we have. We have 1, 2, 5, and 0, 1, 2, and 0, 0, 0. Okay. So what we have over here now, the last column doesn't have a leading one. Leading one is over here and over here. So x3 is free. x3 is free over here, right? And then so x2 is going to be -2x3, because this equation is x2 plus 2x3 is equal to 0. And x1 over here, let me move over here a little bit. So x1 is going to be equal to -2x2 minus 5x3. And so this is going to be -2x3 back substitution and minus 5x3. So that's 4x3 and minus 5x3. And then we have -x3. So in terms of vector form, we have x1, x2, x3 over here is equal to -x3 and -2x3 and x3, like this. If we pull out x3, this is the vector we have, or we can say, right, we put s over here, and it's -1, -2, and 1. We only need to take one eigenvector, so we say eigenvector over here is simply -1, -2, 1. We will finish the last part of it in another video because this is getting too long.